Okay.
Okay. So for this session of the Albert Einstein's Enjoyers Quantum Reading Group, we're gonna have a talk from our host, Zachary Bradshaw, who is getting his PhD in mathematics at Tulane, which is wonderfully convenient because this should be a math-based section of Nielsen Schwang. So without further ado, take it away, Zach.
All right. Let me actually pull this back up. Okay. So I am going to start off with something that's not in Nielsen Schwang or KLM. So I'm going to actually build up this notion of a Hilbert space because I think it's kind of important, because eventually we will run into other abstract algebraic structures like groups, and it's useful to see how they come along. So let's see if my OneNote will cooperate with me. Maybe not. OneNote, please.
Excuse us, we're having technical difficulties.
Okay, well, maybe I'll just move to the next page if this doesn't work. But so essentially what you do is you start off just from a set, which is something hopefully we're all familiar with. So a set is just like a collection of elements, we call them. Could be, the numbers 1, 2, 3, could be ABC, could be a circle, a square, maybe a heart, and a 3, and letters A and B, whatever. A set can be just a collection of items that you throw together. But sets by themselves usually aren't very interesting. We want to put some kind of structure on them and then study the structure itself. And so one way to do that, and certainly not the only way to do it, is to add a group structure. So I'll talk about that in a minute. And after that, you can move forward. You can put a ring structure on your group. And if that ring has certain properties, then it becomes a field. And then we're able to talk about vector spaces over a field. And from then, we can put an inner product on the vector space. And whenever that inner product is complete, what we have is a Hilbert space. So that's kind of the outline of how this goes. So let me try to put that all together. What?
Oh,
let's see if that works. That is not what I had. Yep, it just disappeared. All right, whatever. Okay, so again, a set is just a collection of elements like 1, 2, 3, maybe A, B, C, or maybe even a circle, a square, triangle, the number 3, maybe A, B, I don't know, 42,000 if you want. They're just a collection of things. But some sets that we're gonna use a lot are the natural numbers, which are 0, 1, 2, 3, all the way to infinity. These are also called the counting numbers. And then the integers, which is just plus or minus all of the natural numbers. So if you're not familiar with set notation, the way you read this is the set of all of plus or minus all numbers n. And this means such that n is in the natural numbers. So the integers are the set of all plus or minus n such that n is a natural number. Okay, so if you wanted to write that out, you could write it this way. I don't know, -2, -1, 0, 1, 2, like this. Okay, so from there you can build the rational numbers. The rational numbers are all the numbers of the form m over n, such that m and n are both integers. So these are things like 1/2, -3/2, and so on, all these fractions. Then we can build the real numbers, and their construction is actually a little complicated. So if you take like a real analysis class in the math department, you'll see it. But essentially what they are is they are limit points or limits of sequences of rational numbers. So if I give you a sequence of rational numbers and it converges, the thing it converges to is a real number. And that's how you build the real numbers. So the fact that it's true that all real numbers have a rational or sequence of rational numbers converging to it is referred to as the property of denseness. So Q is dense in R, the rational numbers are dense in R. This means that every real number has a sequence of rational numbers converging to it. But at the end of the day, what we are concerned with is the complex numbers, which are the numbers of this form. So the complex numbers are all the numbers of the form x plus iy, where x and y are real, and I squared is defined to be -1. So if you like, you can take I equal to the square root of -1. But this is the important property that we care about. So what can you do with these? Well, when we start to give the complex number some structure, we can do some addition. So we can add this complex number with this one. So x plus x prime plus I y plus y prime. So you add like terms, anything that's real, you add together, anything that's imaginary, meaning it has an I in front of it, you can add together. So the complex numbers have all kinds of nice properties. Another thing you can do is multiply. If you have a number lambda in R, then you can multiply lambda times the complex number. This is lambda x plus I lambda y. You can take conjugates, so the way we denote that is with a bar. Sometimes we use a star instead. And the way we define this is wherever you see an I, you give it a minus sign. Okay, so in the imaginary part, you flip the sign of it. Okay. But we are getting a little ahead of ourselves here. So the question is, if I have a set, what can I do with it? And what you want to do is you want to add some kind of structure to it. And one of the easiest ways to add structure is to create something called a group. So a group is, so it's a set, let's call it G, with a binary operation. So I'll call it, let's just use addition. So let me just assume it's addition for a minute. So this plus takes two elements of G and spits out another element of G. Okay. So I'll give an example in a minute, but this is what it means to be a binary operation. It means you take two elements and you spit out one. And it needs to satisfy three properties. One, it needs to be associative. So if G H, and K are all elements of G, then we need G plus H plus K to be the same thing as G plus H plus K. So it doesn't matter what order you add the things in. So again, addition here is not the only operation you can put on a group. You can put multiplication, you can put composition, functions, for example. So any operation that's going to satisfy these three things here. So you need an identity. So the identity is an element we usually call E in the group, such that for any other, maybe I should say, so we need an identity. So we need that there exists an element E in G, such that for any other element, let's call it G, E plus G is equal to G. And we can also do it the other way, G plus E. So if your group is the group of integers, then obviously under addition, obviously your identity is going to be 0. If your group is the real numbers except for 0, under the operation of multiplication, then your identity is going to be 1, right? Because 1 times anything will just give you whatever the other thing is. And the last thing we need is the existence of inverses. So for any G and G, we need that there exists an H and G, such that G plus H is the identity. And the same holds for the other direction. So if we're talking about the integers, then the inverse of G would be minus G, right? We're talking about the real numbers with multiplication, then the inverse of, I don't know, let's say 5 would be 1/5, right? It's the reciprocal. So let me zoom out. So anytime you have a set with an operation, which I just called plus here, that satisfies these three properties, what you have is called a group. Okay, so groups pop up everywhere in mathematics, and occasionally you'll see them in quantum computing, maybe even quantum information theory, I don't know. Yeah, a subfield of mathematics that's particularly useful to anything quantum mechanics really is representation theory, which is so it's a way to represent elements of a group as usually matrices. But let's not get into that. Yeah, we can talk for hours on this. Okay, so the next thing you can do is put a ring structure on your group. So rings and fields. So I don't want to go into too much detail because we don't have too much time. So essentially rings are groups, but with multiplication. Multiplication 2. So that's not exactly right. It needs to satisfy a few other properties. So it needs to be distributive. So maybe I'll say so if I have a ring R and I have 2 elements of the ring, then I need X plus Y times, oh, I need another one. Let's say z times z to be the same as x times z plus y times z, right? And I need to be able to go the other way as well. Among some other things, there needs to be an identity element, right? Which is essentially 1, right? There needs to be some element that when you multiply, you just get back the original thing. And lots of other things. But if this multiplication is commutative, which means x times y equals y times x, and inverses exist, so that means for every x, there's a corresponding inverse, right? Which maybe we might write as 1 over x. Then what you have, so if these two things are true, then what you have is a field. Okay, and this is something we do care about. So we'll never look at rings by themselves, I don't think, but a field is something we do care about. An example of a field is the real numbers, right? The multiplication is commutative. 2 times 3 is the same thing as 3 times 2. A times b is the same as b times a. And every element other than 0 has an inverse. So maybe I should, so except 0. Obviously, you don't need a multiplicative inverse to 0. Those don't exist. And another one is the complex numbers, C. And these are the two that we'll really care about, R and C. Others do exist. There are finite fields, for example. It's usually the integers modulo something, I think a prime. But these are the two that we'll really care about. Okay. So that brings us to vector spaces. Okay, so a vector space is, well, I didn't say what abelian means. Yeah, so a vector space is an abelian group. I'll say what that means in a second. With a scalar multiplication. So what I should have said here was vector spaces over a field, because we need two things. We need elements of the vector space. So for example, an example of a vector space is, let's say R2. That's a little more descriptive. So R2 is the set of all pairs x, y, such that x and y are real numbers. And it's a group under addition, right? So R2 with addition is a group. And this group is commutative. What that means is, if I take x, y, and I want to add, whoops, that should be a comma, x prime, y prime. Well, the way we do that is we add component-wise, so it's x plus x prime, y plus y prime, and I can switch this around. Right. This is the same as x prime plus x, y prime plus y, and then I can take it out again. So this is, so take them apart, x prime, y prime plus xy. So adding this way is the same as adding this way. So essentially, commutative just means a plus b is equal to b plus a. And if you are a mathematician, then you call a commutative group an abelian group. So abelian is synonymous with commutative. Okay. So what's a scalar multiplication? Well, we need a second thing. We need a field, right? So R2 is a vector space over a field. I should say the field R. What this means is R2 is an abelian group, and we also have a scalar multiplication. So if we take some number lambda in R, we can multiply it. We can multiply, say x, y is in R2, lambda times xy, and this is lambda x, lambda y. So a scalar multiplication is a map, which we usually just call a dot. And what does it do? It takes an element of my vector space, which is R2. I should go the other way. It takes an element of my field and an element of my vector space and spits out another element of the vector space. Yeah. So here's my field. Here's my vector space. And there's my vector space again. So again, the scalar multiplication has to satisfy certain properties that we really like. And you can kind of see what they are just from the example. So we need distributivity. So lambda times x, y plus x prime, y prime. You want to be able to distribute this to each term. You want to be able to do it from the right as well. You need the identity element in the field. Needs to do what you would think it would do. So basically, for a vector space, everything that you would want to do, other than multiply two vectors, is written inside of the vector space. It's all fine. Okay. But in quantum mechanics, we want even more structure. So I just said in a vector space, you can do pretty much anything you would want to do, except multiply two vectors. You need more structure for that. So if I take, so let me just take, so let's let V be a vector space. I want to have some operation, I'll denote it like this, which takes two elements from my vector space and spits out a number. So the number belongs to the field that the vector space is over. So in quantum mechanics, we usually want that to be the complex numbers. Okay, so what it does is, well, you already know one. You already know an inner product. So let's take R2 again. If you've taken calculus, then, or calc 3, I guess it would be, the dot product. So the dot product is an example of an inner product. So you can take xy and take the dot product with AB. And what this gives you is x times A plus y times B. So this is maybe an example you should keep in mind. So what makes an inner product an inner product? Well, it needs to be linear. So let's say V or U and V are elements of my vector space. Then U plus V, I need a third one, let's call it W. U plus V inner product with W needs to be equal to U inner product with W plus V inner product with W. And if lambda is in my field, then lambda u v, let's see, in quantum mechanics, we actually want this to be the real linear coordinate. We want this to be equal to lambda times u v. And we want this to be conjugate symmetric, meaning if we flip this around, what we have to do is conjugate the resulting number, and then these two things are equal. And lastly, we want uv to be greater than or equal to 0, and we want this to be equal to 0 if and only if. Oh, sorry, that should be VV. That should be equal to 0 if and only if V equals 0. Okay, so if you have some operation that takes two vectors and spits out a number, and it satisfies these properties, then what you have is an inner product. And so finally, that gives us a Hilbert space. So in finite dimensions, which is all we're going to deal with. So in finite dimensions, a vector space, sorry, an inner product space is a Hilbert space. So when you move to infinite dimensions, you got to be a little more careful. What you require is that your inner product space is complete, which is just another technical piece of information. So if you have a sequence that has the property of being Cauchy, which means that the elements sort of move in together, so that the sequence kind of, if you think about a graph and you kind of plot the points of the sequence on a graph, that sequence kind of closes in. It looks like it's converging to something. Then that does in fact converge. So if that's true, then your Hilbert space is complete. But we're not going to be really worried about that. In finite dimensions, an inner product space is a Hilbert space. And our Hilbert space is always going to be over C. So we'll usually denote it H is a Hilbert space over the complex numbers C. So we'll always take this to be true. Okay. So I have to mention something about the Dirac notation now. So if you've taken multidimensional calculus, then you've probably seen, or physics class, you've seen the notation V with an arrow over it to mean a vector, right? So usually we work in R3. So this would be like Vx, Vy, Vz, right? So in quantum mechanics, we use the Dirac notation. And so essentially all that means is instead of an arrow, we put the V inside of this little, I don't know, what do you even call this? We call this a ket, but I don't know how to describe this symbol. Holder, placeholder, sure. Yeah, and it sort of means the same thing, but now we usually think about our vectors, we try to get used to think about our vectors as columns now. So those are all subscripts. I know it doesn't really look clear, but okay. So whenever you have a vector space, there is a corresponding space called the dual space, which consists of what are called linear functionals. So a linear functional is just a map that takes a vector and spits out a number. So it takes a single vector and spits out a number. So for example, it might take the vector 1, 2, 3, and maybe it spits out, I don't know, the sum of them. We'd have to check if that was linear, but anyway, it might do something like that. So in quantum mechanics, we denote this in the following way. So a linear functional we denote with the same symbol, but in the opposite direction. We call that a bra. So this we call a ket. This we call a bra. So when we put these together, we usually drop the second vertical line. And what we get is an inner product. So this is the inner product of V with itself. And I am glossing over a lot of math here just because the book glosses over it. And I'm trying not to add too much to this. But highlights, so if you have a basis, so if maybe E1 through En is a basis for your vector space, then there's a corresponding dual basis, which we usually call F1 through Fn. For the dual space, which a mathematician would usually write as V star, but that can be confusing in quantum, and I don't think there is a notation in quantum mechanics.
Let's just call it.
Yeah, call it whatever you want. I don't care. But anyway, so the Hilbert space we care about, just to put this all in perspective, is usually C2, which has the basis 1, 0, 0, 1. And this is a vector space over C. Okay. So we allow multiplication by complex numbers. Okay, and the dual space you can think about as so the dual space. Well, this would be C2 again, but this time we would think about them, our basis vectors, as rows. Right. And when we inner product this row with this column, well, that would just be the dot product. So that's the way to think about it. But again, let's switch over to the Dirac notation. So for my Hilbert space, which is C2, the basis would be, we usually call this, so one basis is 0 and 1. Where this is the column vector 1, 0, this is the column vector 0, 1. And the dual basis would be denoted this way. Okay. So there really is no substitute for learning linear algebra from an actual linear algebra text, but we'll try to pick up the highlights here. So the dual basis has the property that, if you take 0 inner product with 0, what you get is 1. Inner product of 0 with 1 is 0. 1 with 0 is 0, and 1 with 1 is equal to 1. So in general, how do we define the dual basis? Well, if E1 through En is a basis for V, then F1 through Fn is the basis for the dual space such that Fi of Ej is equal to the Kronecker delta Ij. So remember, the dual space is the space of linear functionals. So this guy, it takes a vector as an input, which is what Ej is. And if this thing is always 0 when I is not equal to j, so remember this is 0 for I not equal to j, and 1 when I is equal to j. So if it's 0 when I is not j, and it's 1 when I is j, then what you have is a dual basis. Okay. Yeah, so maybe I should move on from here. Yeah, so I'm really running out of time here. Okay, so we have a Hilbert space. Great. What do we do with it? We like to act on Hilbert spaces with linear operators. Okay, what does that mean? Well, a linear operator, it takes an element of the vector space and spits out another element of the vector space. So in general, they could map between two different vector spaces, but we'll usually only care about linear operators that map from our Hilbert space to our Hilbert space. So maybe I should take out these V's and put an H here and an H here for Hilbert space. So the linear property just means that if A acts on, so let's say alpha 0 plus beta 1, for example. So alpha and beta are both complex numbers here. Then this is the same thing as alpha times A acting on 0 plus beta times A acting on 1. So essentially the linear operator distributes and it moves through scalars. So the scalars being the complex numbers here. Okay, so that's a linear operator. Why do we care about these? Well, maybe I shouldn't say why yet. So in section 2.2, we get into the quantum mechanics, which will explain, why we care about the linear operators. But anyway, so there are some examples that we should keep in mind. So let's take our Hilbert space to be C2 again. Remember, this is just the set of all complex column vectors xy, such that, so xy are in C. And this is a vector space over C, so we allow multiplication by complex numbers. And the inner product here is just sort of the dot product, but whenever we do the dot product, we also have to conjugate one of the vectors. So in the Dirac notation, this is the set of all elements of the form alpha 0 plus beta 1, such that alpha and beta are in C. Okay, so I'll stick with the Dirac notation now. So here's my Hilbert space H. And we can usually think about an operator as a matrix. So all linear operators have a matrix representation. Okay, so the way we use that is we convert from a Dirac notation back to the column matrix notation, do the multiplication, and then go back to the Dirac notation. We can do that, or we can figure out how the matrix acts on the basis elements 0 and 1 here, and then deduce how it acts on any vector after that. So let me show what I mean. Let me introduce the Pauli matrices. Okay, so after I do this, we'll, I guess, stop here. Okay, so the Pauli matrices, sometimes we include the identity in this. The identity is the matrix 1, 0, 0, 1. So again, we're thinking about the Hilbert space C2 here. And we have the X matrix, which is 0, 1, 1, 0. We have the Y matrix, which is 0, minus I, 0. And we have the Z matrix, 1, 0, 0, minus 1. Hopefully I got all those right. Yeah, okay. So we can ask the question, well, how does the identity act on 0? Well, in the matrix notation, this is 1, 0, 0, 1. And this 0 ket is the same as the column vector 1, 0. And so now we just do the matrix multiplication. We multiply the row by the column, we get 1, 0. And we can convert back to our ket notation. This is 0. So we can do the same thing for 1. And we'll get exactly the same thing. We'll just get our input back, which is what you would expect, being that the identity is called what it is. Okay, so how do we deduce how I acts on an arbitrary vector from this? Well, an arbitrary vector can be written as alpha 0 plus beta 1. And we know that I is a linear operator, so we can distribute like this. I have an extra parenthesis here. And the identity we just figured out does nothing to 0, and it does nothing to 1. And so this gives us back alpha 0 plus beta 1, which is our original state psi. So I does absolutely nothing to any state ever. It's the most uninteresting operator you can think of, other than maybe 0. But even that does something. So yeah. So one that's maybe a little more interesting is the X operator. So what does it do to 0? Well, X is the same as this matrix. 0 is the same as this column vector. We multiply them, we get 0, 1. And this is the same as the ket 1. And it does the opposite to the ket 1. It gives you 0 if you do the multiplication. So then what you get on an arbitrary state, alpha 0 plus beta 1. Well, again, you can just distribute this and move past the constants. This is alpha 1 plus beta 0. So the effect that X has on an arbitrary state, alpha 0 plus beta 1, is to flip-flop the amplitudes or the coefficients of the basis elements. Okay, so I'll just say what Z does quickly. This is alpha 0 minus beta 1. So just introduces a minus sign to the coefficient of the one basis state. Okay. All right, so I think I have to stop there. Yeah, because we've used up quite a bit of time. But yeah, so maybe I will continue this next week. I know I've said mostly stuff that I think most of us already know. But if anybody hasn't taken linear algebra, hopefully this was helpful. But next time we'll get into the actual interesting stuff. So anybody have any questions? All right.
All right. I was thinking quick. Answer Lisa's question.
Okay, Lisa. So any vector space, for any vector space, you have to define it over a field. So let me go back to the OneNote here. So remember, a Hilbert space is a vector space. So the Hilbert space H is a vector space with an inner product. All right. So there's fact one. And what's the definition of a vector space? Well, a vector space it's an abelian group, which also has this scalar multiplication. But where does the scalar multiplication come from? Well, so the scalar multiplication we usually denote with a dot, right? And it takes an element of a field. So C, for example, and an element of the vector space, and it spits out another element of the vector space. So in order for this thing to be defined, you need a field. So that's true for any vector space. A Hilbert space is just a special example of a vector space. So that's why you need your field. Okay.
I was just asking intuitively, can you just think of a ring as being a group twice or two ways? Because using the word like multiplication when you're talking about the binary thing is a little bit confusing.
Yeah, so it's actually not the case. You can't think about it as a group in both ways because the thing I kind of glossed over were the axioms that you need for something to be a ring. So the axioms that the multiplication needs to satisfy. Let's see, what are they? So it turns out that you don't need all the axioms of a group for the multiplication operation. So what do you need? You need associativity of the multiplication. So that's one of the group operations.
You don't need an inverse, right?
You don't need inverses. When you have an inverse and the operation happens to be commutative, then you have a field. But it's not true that all rings have a multiplicative inverse. So actually, it's not a group twice. It's only a group once and possibly twice. Isn't it that you don't need the inverse multiplication because of 0? So 0 is actually a special case. When I say you need a multiplicative inverse to be a field, I mean for everything except 0. Yeah, so 0 never gets a multiplicative inverse, but you do need a 0, right? You need the 0 for the abelian group because that's the identity of the group. You wouldn't have a group if you didn't have the 0. Okay. But yeah, so 0 is always a special case.
I guess you can think of the reason you don't need an inverse for 0 is because it's an identity. You don't need an inverse to undo the identity because the identity didn't do anything to begin with. Right?
Well, in this case, so for the 0, you would be asking for a multiplicative inverse, right? But all the 0 does is turn everything into 0. And
Yeah,
so there's
that's true.
absolutely no way you could possibly
Oh.
construct an inverse to that.
It's not an identity under multiplication. Yeah.
Right,
that's
yeah.
My bad.
Yeah, so the identity under multiplication would be like 1 in the real numbers, right? And that does have an inverse, it's itself. Yeah, okay. Any other questions? I know the first half of that was maybe a little abstract, but hopefully you got something from it.
I feel like if you've seen it before, you're like, okay, well, it's a review. But if you've never seen it before, it's like, what, a week of abstract algebra?
We blew through, I think, 2 semesters of abstract algebra there.
I don't know about the semesters, but yeah, like a good bit of abstract algebra. Very good.
Yeah, groups and rings you learn in the first semester of abstract algebra. Then you get to fields and vector spaces and whatnot in the second semester. And there's lots of stuff in between. Yeah, you might touch on it, but you don't really get into like Galois theory, for example. So the second one. Yeah, anyway, any other questions? Okay. What's that? Oh, yeah. Let's see.